Welcome, this is Dr. G, and in this video I will be going over what you have to know for kinematics in 2 dimensions. We're first going to go over how to draw adding or subtracting vectors, and then more importantly, we'll go over how to break down each vector into its vertical and horizontal components so we can add or subtract vectors in actual questions. Now, in order to do this, you will need some basic trig knowledge. If you forgot or if you're rusty, that's okay, I'll cover it in this video. A quick note before we start. Breaking down vectors into horizontal and vertical components is extremely crucial in physics, not just in kinematics, but in later chapters as well, such as dynamics and equilibrium. So make sure you have a good grasp of what's happening here. It will pay dividends down the road for physics, guaranteed. You got this. And let's have some fun. Let's go. Before we go into the drawing of vectors and breaking down vectors into its individual components, let's quickly compare the differences between scalar quantities and vector quantities. First, scalar quantities only consists of magnitude, or a numerical value to represent its size. For example, I can say that the mass of an apple is 1 kilogram. I don't have to say that it's 1 kilogram north or 1 kilogram to the left, it's just 1 kilogram. Scalar quantities are also in 1 dimension, meaning that it doesn't have to worry about the different planes, whether it's vertical plane or horizontal plane. Everything is in 1 dimension when you're talking about scalar quantities. On the other hand, for the vector quantities, it consists of both magnitude and direction, so you have to include and take into account of direction when you're doing vector questions. And vector quantities can also be represented in 1 dimension, just like scalars, but it can be represented in 2 dimensions as well. In which case we can look at this graph with the x and y axis to represent 2 dimensions. Alright, so let's talk about vector quantities. Now, we know that vector quantities include both magnitude and direction, so we can represent it using an arrow, because an arrow covers both aspects of vector quantities. The direction aspect of vector quantities is represented by which way the arrow itself is pointing, and the magnitude aspect is represented by the actual size or length of the arrow. As you can see, here we have a bunch of different arrows with different sizes and pointing at different directions, all representing different vector quantities. Now, one thing to note here is you will learn vector quantities at first by drawing arrows and pointing them at different directions and whatnot, but afterwards, when you're doing the actual kinematics or other chapters, they will give you the vector quantities in words and basically telling you the numbers of the magnitude and direction. You don't really need to rely on which way or how long the arrows are pointing. This is strictly as a way to introduce vectors and teach you how to draw them and connect them when we add or subtract. Okay, let's take a look and see how we can add these 2 vectors here. There's just one simple rule when you're adding vectors. You have to connect the vectors base to tip or head to tail, whichever way you want to think about it. So first, let's draw the yellow vector, and then we're going to now add on the red vector onto the yellow vector by attaching the base of the red vector onto the tip of the yellow vector, like this. Now we can draw the resulting vector sum. We start that final vector at the original starting spot, which is the base of my yellow vector, and we go all the way to the very end, which is the tip of my red vector. So that green vector you see here, that is the answer, that is the vector sum. We can subtract vectors as well, although personally I prefer to think of it as adding a negative version of that vector. So now how do we add a negative version of the red vector? We just flipped the vector upside down. So we can say it's the yellow vector plus the flipped version of our red vector. And now we just do what we did before. We start with the yellow vector, connect the red vectors head to tail, and then finally draw in our resulting vector sum, the green one here, starting at the original starting spot of my yellow vector's base, all the way to the red vector's tip, and that is our resulting vector. And of course, we can add and subtract multiple vectors, not just 2. As you can see here, we have 3 vectors. Now give it a try, pause the screen, and come back when you're ready. Alright, so let's start with the yellow vector here, and we're going to connect the red vector onto the yellow vector, head to tail, like that. Now we're subtracting the blue vector, which means we're adding the negative version of that blue vector, which means we're going to flip the blue vector and then add it onto our red vector, just like so. And then now we can draw the resulting vector sum, starting again at the very beginning, which is the base of my yellow vector, going this time all the way to the tip of my blue vector like this, and that is the final answer. Okay, so now we feel good with adding and subtracting vectors by drawing them out, connecting them, and drawing the resulting vector sum. However, it's a very small portion of kinematics and physics in general. You will mostly deal with adding or subtracting vectors when they give you numerical values instead. Recall that vector quantities include both magnitude and directional components. Well, that's both covered when they give you these numerical numbers. The direction part is covered in the 30 degrees north of east for the yellow vector and the north for the red vector. That's the direction. The magnitude is covered in the actual velocities. Remember, not speeds, because speed is a scalar, but in the numerical velocities of the yellow and the red vectors respectively. Now, before we can actually add these two vectors by looking at just the numbers, notice that the arrows are not that even important anymore. We don't even need the arrows. We can do this question with just the numbers they give us. But before we can do that, we need to review two things. First is just to get comfortable with how they describe direction in physics. For example, what does 30 degrees north of east actually mean, and how can we turn that into an actual triangle where we can break down the components? And secondly, we must review a bit of trigonometry, mainly the Pythagorean theorem, as well as the three trig ratios of sine, cosine, and tangent. In physics, aside from the usual navigation of left, right, up, and down, sometimes if there's any type of diagonal motion involved in two-dimensional questions, they will use the compass navigation of north, east, south, and west. In terms of the signs, it's pretty typical. North or up, east or right are both positive, whereas south, which is down, or west, which is left, are both negative, same as math. Let's now try to draw this 30 degrees north of east on our diagram. So first, because it's north of east, we know for sure it's going to be in the top right quadrant, or quadrant 1. So we're just going to draw the vector or an arrow pointing that direction, starting from the origin. It doesn't have to be precise. You don't have to draw it slightly closer to the east because it's 30 degrees. I personally prefer to just draw it right down the middle at a 45-degree angle for all of these vectors, because nothing's going to be drawn to scale and your teacher doesn't expect you to do so. Now notice it says north of east. So in that case, we always start at the east or horizontal line, and then we move towards north, and that's our angle is formed. So again, our angle starts at the east and then moves towards the north direction until it hits our vector line, and then we can label the angle as 30 degrees. Once we've labeled our angles, we can actually make a triangle that includes the angle here. So from this diagonal vector I can have a horizontal component, or the x component, and a vertical component, or the y component, and together now I have a right triangle with my angle of 30 degrees within the triangle. Now some of you might be thinking, well, what if I want to do the vertical component first of y and then the horizontal component later? Is that okay as well? And my answer is yes. These two triangles are really just flipped versions of each other, but I prefer the previous example. Why is this going to be a bit trickier than earlier? Well, first of all, the angle that we have, the 30 degrees, is technically not even in this version of the triangle, is it? Now, I know, you might be thinking, well, based on the laws of alternate interior angles, then the 30 would be up there, right? Or based on the complementary angle rules, you can say that this would be 60 degrees right there. Again, true, but later on when you're doing physics questions and the diagrams get pretty nasty, you really don't want to be drawing triangles where you have to figure out the angles on your own on the side, because that's more room for mistake. So my recommendation is, when you're making triangles, always try to make it so that the angle that you have is within the original triangle, so you don't have to do some crazy stuff to figure out what the angles are. Alright, let's try this one here. 78 degrees west of south. First of all, between west and south, we can draw our vector right down the middle. And now it says west of south. So that means we start on the vertical south line and we move towards the west until it hits our vector like this. And we can label that angle as 78 degrees. Now we can break this into its vertical component of y and the horizontal component of x to complete our right triangle. Alright, so now given the directions of our vectors, we're able to turn it into a right triangle. The next step would be, of course, to play around with the right triangle and get what we need to get to answer the question, and the tool to do that would be trigonometry. There's two aspects of trigonometry you have to know for physics. The first one is Pythagorean theorem. So for a right triangle, we can label the sides as A and B. It doesn't have to be that way. You can flip it around, or you can use really any letter you want. but the hypotenuse is always going to be here, and it's the longest side. The Pythagorean theorem states that a squared plus b squared equals c squared, and with this Pythagorean theorem, you're able to figure out any side as long as you know the other two sides of a right triangle. The second part of trig you have to know for physics is the three trig ratios of sine, cosine, and tangent. Let's take this right triangle for example, and let's say that the angle here is 30 degrees. We can label the sides as x for the horizontal, y for the vertical, and this hypotenuse for the hypotenuse. Again, earlier I said you don't have to use a, b, and c, you can use whatever letters you want, so it's a good idea to use x for horizontal, y for vertical. It will help you with math as well. Okay, now with respect to the angle of 30 degrees, the x side is actually the adjacent side, and the y side is the opposite side because it's across from the angles. Having said that, now there's a mnemonic you probably know as SOHCAHTOA, and that means the sine ratio of the angle, or sine 30 degrees, is always equal to opposite over hypotenuse, and since our opposite is y, it's going to be equal to the y over hypotenuse. The cosine ratio of 30 degrees would be the adjacent over hypotenuse, or the x over hypotenuse. And then finally, the tangent ratio of the 30-degree angle would be the opposite over adjacent, or y over x. We can also use the three trig ratios to find a missing angle, given that we know at least two of the three sides of a triangle. To find an angle using sine, we would actually use the inverse sine of opposite over hypotenuse, or in this case, y over hypotenuse, and that'll give us the angle. With cosine, it'll be the same thing, except it will be the adjacent over hypotenuse, or x over hypotenuse. And for tangent, it will be the inverse tangent of the opposite over adjacent, or y over x, to find the missing angle theta. Alright, now that we know about the directions and the trigonometry portion, we can tackle this problem of adding vectors now. First of all, when we're adding these vectors, you can't just add the 20 meters per second velocity to the 25 meter per second, because the 20 meters per second is slanted, it's diagonal, and the 25 meter per second is going up and down. Generally speaking in physics, we don't like diagonals, so we always want to break down our diagonal vectors into the horizontal x and the vertical y components. Now, when you first start kinematics, and for the majority of kinematics, you're not going to need to add different vectors together numerically like we're about to do. That's more for momentum and collision questions that you'll do later on. But you do need to break down diagonal vectors into its horizontal and vertical components, so we might as well learn the whole thing right now. Let's take a look at the information given. At this point, it's pretty clear that we don't really need them to draw us these arrows. 20 meters per second, 30 degrees north of east, we already know it's going to be pointing to the top right corner because that's where northeast is. For the red vector, we already know that north points up, so that arrow pointing up doesn't give us any information. So everything we need is actually in the numbers, the magnitude and the direction is already in there. There's also different ways of doing these questions. Some teachers like it for you to actually draw and connect the vectors together and then use a little bit more advanced trigonometry like the sine law or the cosine law to figure out the answer. I don't like it because it's not very applicable to other parts of physics. The best way to do these questions is to take any slanted vectors or any diagonal vectors you have, break it down to its x and y components, and then add up all the x components you have, add up all the y components you have, and then you'll have your overall x and y component. Alright, so we're going to start with one vector at a time. We're going to start with the yellow one here. Again, we don't really need the arrow because we could have just drawn it to the first quadrant anyway, but let's say they gave it to us here, and we can see that 30 degrees north of east means we're starting off on the east and then moving north until we hit our vector, and that is our 30 degrees. Now we can turn this into a right triangle with a x component that's horizontal and a vertical y component. Again, with respect to the angle, my x component is the adjacent side and my y component is the opposite side. For the hypotenuse, we actually know what it is. We know that our hypotenuse is 20 meters per second because that's my diagonal yellow vector. Okay, so now we have to figure out what is the horizontal velocity, the x component of that 20 meters per second overall velocity, and what is my y component or the vertical component of that 20 meters per second velocity. So let's do the x first. The x is the adjacent side, and we know the hypotenuse already, so it will be wise to pick a trig ratio that includes both the adjacent, because we want to know the adjacent, and the hypotenuse because we actually know the hypotenuse. So which trig ratio has adjacent and hypotenuse? So ka toa, so that's got to be the cosine. So we can write it as the cosine of the 30-degree angle is equivalent to x over hypotenuse. We don't know what x is, so we'll leave it as x, but we know the hypotenuse is 20, so we'll replace that with that. And now it's just algebra. We can isolate the x by multiplying both sides by 20, and now we can crunch it into our calculator. 20 times the cosine of 30 degrees is going to give us 17.3 meters per second, and that is the horizontal component of my overall 20 meters per second velocity. Now we're going to do the exact same thing for the y, or vertical component. The y is the opposite side, and we know the hypotenuse, so let's use sine. Sine is equal to, or sine 30 degrees is equal to y over hypotenuse. And we can replace the hypotenuse with 20 because we know that's what it is. Isolate for y, crunch into our calculator, and we get the y component as 10 meters per second. So now this yellow diagonal vector of 20 meters per second is no longer useful because we've broken it down to the x component, which is 17.3, and the y component, which is 10 meters per second. Note that because my x component is going to the right and my y component is going upwards, they're both positive. If this was to be pointing the other direction to the left or downwards, then I will have to make either x or y negative depending on which way it's pointing. Now let's focus on the second vector, the 25 meters per second north, or the arrow pointing up. Again, we don't really need them to give us this arrow because we already know north is pointing up. But here it's going to be a lot easier because this is not diagonal, meaning this only has a y component, doesn't it? This has no x component, so we can't even break this down or make this into a triangle. So this vector is solely the y component. So the y component here would just be the same as the overall vector, which is 25 meters per second. Again, it's positive because it's going upwards. Let's see what we have now. For the yellow vector, we've broken it down into its x and y components of 17.3 and 10 meters per second respectively. For the red vector, we know it's only the y component of 25 meters per second. So now we can add up all the x components and add up all the y components for a total overall x and overall y component. For the x, there's nothing to add because we only have the yellow vector that has an x. The red one doesn't even have an x, so our overall x vector will just be 17.3. For the y, we're going to add up both the 10 and the 25 meters per second. Remember, they're both going up, so they're both positive. So we're just going to add those two positive numbers together to give us a total of 35 meters per second for my overall y vector. Now that we know the overall x component and the overall y components of our overall vector sum, we can combine the x, or the horizontal vector, along with the y component, or the vertical component, and that should give us the overall vector component of this purple vector, right? Remember, we start from the very beginning, which is the base of the x arrow, and we go all the way till the end, which is the tip of the y arrow. So this purple vector is the resulting vector of when we added our yellow original diagonal vector with our upwards red vector. The question is, what is the magnitude and what is the direction of that purple vector? Let's deal with the magnitude first. To find the magnitude, we're basically looking at a Pythagorean theorem question, right? So we know the 17.3 side and we know the 35. We're looking for the hypotenuse. So we just do a bit of calculations of the Pythagorean theorem and we end up with an answer of 39 meters per second for the magnitude of our overall vector. Now comes the question of direction. What is the angle here? This angle should be north of east because we're starting at the horizontal and we're moving upwards towards the north until we hit the vector. So to find an angle, we have to go back to our trig ratios of sine, cosine, or tangent. Notice here, we know all three sides, so we can really pick any ratio we want to figure out this angle. Let's say we use sine. Okay, remember, when you're finding angles, you have to use the inverse trig ratio. So we'll use the inverse sine. And sine, remember, is opposite over hypotenuse, which is y over hypotenuse. We know both of these, so let's plug it in. Inverse sine of 35 over 39. We crunch that into our calculator, and we get an angle of 63.8 degrees north of east. So we have just officially calculated the magnitude and direction of our resulting vector when we added our yellow and red vectors together, and it is 39 meters per second, 63.8 degrees north of east. Now, it might seem like we did a lot of work there, but it's really not, and it's very systematical. So as long as you break the initial vectors down into their x and y components, and then you add up all the x and y components together, and then you just build it up into a final diagonal, perhaps, vector at the end, that is how we do these questions. All right, here is an example that I want you to try first. Pause the screen, work it out, and then we'll work through it together. Okay, so let's break down the first yellow vector together here. They didn't give us an arrow, but that's okay. We can make our own. Let's do our grid here. And we know that it's north of west, basically northwest. So we know the arrow has to point in the northwest direction here. And we know that the vector itself is 6 meters per second. So we can label it a 6 for the diagonal here. Now for the angle, we're going north of west. That means we're starting west, and then we're moving up towards the north direction until we hit the vector. So that is our angle of 85 degrees. And once we have the angle, we can put in our x and y components to make a triangle. Once we have our triangle, I recommend making like a T-table to organize your work for the x and y components so they don't get mixed up and it won't look confusing. So let's do the x component first. We know that the x component is the adjacent. So we're going to use cosine here. It will be cos 85 is equal to adjacent over hypotenuse, or x over hypotenuse. We know the hypotenuse is 6, and we solve for the x, and we get x is equal to negative 0.52. Notice I have the negative because our x arrow is pointing to the left, and left always means negative. For the y component, we pretty much do the exact same thing, except we use sine, and we're going to end up with our y component of 5.98 meters per second. On to the second vector now. Again, no arrow, but that's okay. We know that it's east of south, which means it has to be somewhere between east and south. So we draw the arrow this way. We know that the magnitude is 12 meters per second, so we can label the 12 right there. And now we're going east of south, meaning we're starting south, and then we're going towards the east. So our arrow should be here, and our angle of 55 degrees can be labeled right there. And now we can finish the triangle by drawing the y and x components. Now, before we go into the components, notice that I crossed out the 55 degrees and I put a 35 degrees on the bottom right corner. That's because once you know two angles in a triangle, you can find the third angle by subtracting them from 180 degrees. But why am I doing this? Well, if I stuck with the 55 degrees, then my x actually becomes the opposite side and my y becomes adjacent to the 55 degrees, which means I have to use the sine ratio for x and then the cosine ratio for y. That's not a big deal, except on a test situation when it's stressful, you might worry. You might be thinking, wait on, hold on a second. Why am I using sine for x when I've been using cosine for x in my practices? So as a good way to avoid that, it's better to be consistent. So in a situation where you see that the angle is going to make your x component the opposite and your y component the adjacent, just put the other angle. Just use the other angle, which then keeps the x as the adjacent side, which uses cosine, and y as the opposite side, which uses sine. At the end of the day, if you feel like it's easier just to adjust in the question and use sine for x or y depending on the situation rather than changing the angles, that's fine as well. Whatever you prefer, just remember being consistent with how you practice is the best way to make sure you don't make a mistake on a test. All right, now for the x component, because I used the 35 degrees, it is now cosine, and we do exactly what we did before, and we get the answer of x equals 9.83 meters per second. For the y component, it will be sine, and we do exactly the same as we always do, and we end up with y equals negative 6.88. Remember, it's negative because we are going downwards, and downwards is always negative. All right, so now we've taken both of our initial vectors and we've broken them down into their own respective x and y components. So now I can sum up all the x components and sum up all the y components to have my final overall x component of 10.35 meters per second and my overall y component of negative 0.90 meters per second. With my overall x and y components, I can make a right triangle here. Here is my x component going to the right because it's positive, and my overall y component going down because it's negative. So my final vector sum will be this one here, going diagonally downwards. And to figure out what the magnitude of this final vector is, I will have to do Pythagorean theorem. And here it is. We do our Pythagorean theorem and we end up with 10.4 meters per second as our magnitude. All right, and now for the direction, we need to find this angle here. And because we know all three sides, we can use any of the three ratios, but let's use tangent because we haven't yet today. So for tangent, first of all, we have to use the inverse tangent because we're looking for the angle. And tangent is opposite over adjacent, or y over x, which is going to be negative 0.9 over 10.35. crunch that into your calculator, and we get an angle of 4.97 degrees. For the direction, we're starting at the horizontal, going to the right, which is east, and then we're moving downwards towards the south until we hit our purple vector. So the angle should be 4.97 degrees south of east. So the final answer to this vector addition here should be 10.4 meters per second at 4.97 degrees south of east. And this wraps up our video on adding, subtracting vectors, as well as breaking down each vector into its vertical and horizontal component. Now, like I mentioned earlier in the video, there's multiple ways to do vector adding and subtracting. You don't have to necessarily break them down into their vertical and horizontal components. With that said, I firmly believe that this is the best way to do it, just because it not only applies to kinematics, but it applies to so many different topics in physics that you'll deal with later on. If you liked the video, remember to give the video a like, and if you really like the video, feel free to subscribe. And if you have any questions, comments, or topic requests, you can always put it down in the comment section down below.